Section 3, which is the theory of heat, Unit 3, refrigeration and refrigerants. Introduction to refrigeration. Cooling preserves products and provides comfort. In the 1900s, at the beginning, the mechanical refrigeration systems were employed in order to keep products cool. Refrigeration process temperature ranges. High temperature is considered air conditioning comfort. And anything I would just say, just for your reference, would be 40 degrees. 40 degrees or above, we would consider that high temperature as far as the refrigeration air conditioning process. I might want to point out at this point that air conditioning design temperature on evaporator coils or on heat pumps are designed for 40 degrees. So I don't care what system it is. I don't care if it's a mini split. I don't care if it's a split system, package unit. All air conditioning systems are designed for a 40 degree saturation temperature at the coil. If we go below that temperature, what is going to happen is this. We're going to create frost. We're going to have ice buildup. We're not going to have the ability to extract the heat that is coming across the evaporator. Medium temperature is fresh food preservation, such as your vegetables, fruits, things like that. Anything above 32 degrees would be considered medium temperature. Low temperature is below 32. This would be your frozen products, such as your meats, your things that you are going to purchase at the store, prepared foods, which are what they call blast freeze fed items, which are allowed to freeze so that the food product can be preserved for a long period of time. And it's not unusual to store food products in a frozen state for up to a year or more, depending on the item, whether it be meat, vegetables, fruit, that kind of thing. Refrigeration. The process of transferring heat from one place where it is objectionable to where it makes little or no difference. The way I always tell my students how air conditioning refrigeration works is basically we take the heat out of something and put it somewhere else. So, as an example, in the house, if the house gets hot during the summertime, and of course we had a very hot summer here in Southern California, a lot of people have come home to very hot houses or hot places of work. The whole idea behind air conditioning is to take and remove that heat out to the outside of the building where it doesn't create issues for occupants inside. And also in regards to that, on air conditioning, we also deal with humidity, and we deal with other issues. All right, heat contains the warm air in the room, flows into the cooler refrigerator through the insulated walls, also when the refrigerator door is open. Now I need to point out, I don't care if it's air conditioning, refrigeration, the temperature that we are trying to achieve, if we go below 50 degrees dew point, we are going to release the moisture in the air. And if you live out in the desert, such as Palm Springs or Indio, you're typically looking at very, very low humidity levels, in the 15–20% or less humidity. Now, our bodies, our human bodies, are designed to function very well between 46 and 50% relative humidity. So what am I saying? If you take the moisture out of the air, you're going to feel cold, you're going to feel clammy, you're going to have a lot of complaints. And I'm talking about air conditioning. This also applies to the refrigeration process as well. We need to keep some moisture in the product that we are trying to preserve by removing the heat. If we do not maintain that moisture in some way, shape, or form, then the product is going to dry out and it's going to create problems. As an example, if I was to take some celery sticks and put it in the fresh food compartment and set the temperature low enough, I'm sure you've all seen this, the celery sticks will freeze over and get hard, and when they thaw out, then they're really not much good because the moisture has been extracted out of the celery stick, and it creates problems in itself. Okay, take a look at this picture here. In figure 3.3, the cold air falls out of the refrigerator because it's heavier than the warm air located outside. Remember, cool air falls, heat rises. So let's go back to air conditioning for a second. Typically, the best place to remove the heat is where? By the floor? No, it's up by the ceiling because the heat has a tendency to collect up towards the ceiling. Now, what this presents in a way of a problem in the air conditioning comfort level, a lot of houses in recent years have been built with vaulted ceilings. I personally do not like vaulted ceilings. There are people out there that love these expanded high ceiling type houses because it gives the picture that the place is very large and accommodating. However, they are a nightmare to heat and cool. And the reason why I say this, because heat rises towards the top of the enclosure and cold air follows. And so basically in the in the air conditioning season, you are going to have to provide more air to remove that heat that collects towards the top of the vaulted ceilings than in a standard 8 or 9 foot ceiling that you see in a house under most circumstances. Now this also holds true for refrigeration. You open the door, the cold air is going to basically fall towards the bottom, and of course the heat rises towards the top. So typically the warm air is going to enter the top portion, is going to enter up here at this shelf up here, and of course the cold air is going to fall because it is heavier than the warm air. Don't forget, when we open up this door to the room, we're going to dump in that warm air plus humidity. That warm air, if this happens to be a reach-in freezer as an example, is going to collect in the form of water, moisture frozen over, which we call ice, because it's going to be below 32 degrees. And over a period of time, because on a reach-in refrigerator as an example, these shelves are actually the evaporator. And what happens is over time, these coils are going to freeze over, and they are going to become solid with ice. That being said, here's what happens. When that ice builds up on this evaporator coil, your ability to extract the heat from the products that you're storing inside the freezer, as an example, are impacted. In other words, if you're storing a lot of meat in here, or if you're storing frozen vegetables, if these shelves are covered with ice, guess what happens to the capacity to remove the heat from this product? It is going to be reduced big time. So, what's the answer? Well, there's several ways to deal with this. One is to keep the door closed and only open and shut it as little as you need to, and periodically defrost this thing to keep the ice at bay. Or the other thing is to get a frost-free design. Basically what happens is you shut off the compressor, you have electric heat strips, or you have some way of reversing the flow of refrigerant into the evaporator coil to melt the ice off. Of course, once you melt the ice off, it becomes water, collects towards the bottom, and that's what happens. And going back to figure 3.3, the cold air falls out of the refrigerator because it is heavier than the warmer air located outside. The cooler air is replaced by warm air at the top, and this is referred to as heat leakage. Rating refrigeration equipment. Okay, this is very, very important. I don't care if you're in the air conditioning or the refrigeration side of the fence. These are facts that have been established way back when. This is stuff that I learned over 40 years ago when I got into the trade. And these numbers never change. It takes 144 BTUs to melt 1 pound of ice at 32 degrees. So here's where this heat thing comes into play. 2,000 pounds of ice is equivalent to, in this case, 1 ton will require 288,000 BTUs to melt In other words, 144 BTUs times 2,000 pounds. So we always look at everything as a refrigeration ton. This also applies to the air conditioning side of the fence. And what we're talking about is the amount of BTUs to take and melt the ice. In this case here, 2,000 pounds of ice is equivalent to 1 ton. Another way to express it would be 12,000 BTUs an hour. Now, as an example, let's say you have an air conditioning unit that is rated for 3 tons. Well, if it's rated for 3 tons, that means it's going to have 36,000 BTUs of heat removal capability in 1 given hour. You multiply 12,000 times 24, now you come up with 288,000 BTUs. So when you purchase equipment, as an example for residential cooling systems, typically the equipment is going to be rated on the hourly versus the 24-hour basis. The third point, if melting 1 ton of ice takes place in 1 day, 24 hours, 12,000 BTUs must absorb by the ice every hour, 288,000 BTUs, 24 hours a day. And this is assuming the equipment's in perfect operating conditions. We don't have some problems with the refrigerant charge, airflow, things like that. Refrigeration process. Heat is pumped from a cool box to a warm room. Pumping of heat is similar to pumping water uphill. Now, of course, in the refrigeration cycle, we have a compressor, which basically is the pump that moves the refrigerant. Now, I want to go on record as saying all air conditioning compressors that you are going to be dealing with, all refrigeration compressors that you are going to be dealing with, are designed to pump vapor, low pressure vapor. No compressors that are designed to pump liquid refrigerant. Doesn't mean that a compressor can pump certain amounts of liquid refrigerant when there is a low demand. Some of the compressors are designed heavy enough to withstand some liquid going into the compressor. But as a theory of operation, all compressors are designed to pump low pressure refrigerant vapor. And we'll talk more about that in a bit. Air conditioning. A little bit more involved here. Air conditioning pumps heat from the inside to the outside. So if the house is hot inside, we want to get that heat out of the building to the outside. Inside temperature is 75 degrees Fahrenheit, outside temperature is 95. Cooling the evaporator, cooling the indoor coil, temperature 40 degrees. So here's where that 40 degrees. All air conditioning systems are designed for 40 degrees. Please see that, remember that, underline that. That's a very important key. If you don't understand this concept, you're going to have trouble trying to charge a system properly. Check the operational characteristics. 40 degrees is the magic number. Condenser, the outdoor coil temperature is 125 degrees Fahrenheit. Indoor heat travels to the indoor coil. System heat flows from the outdoor coil to the outside air. Now, one thing I've got to talk about here real quickly, of course we'll talk more about this later. Indoor heat travels to the indoor coil. That is provided you have enough return. I'm talking about that big large grill that is underneath the furnace, that big large grill that it takes the heat out of a structure. If your return air system, and I'm talking about air conditioning, is not designed properly, you are going to have problems. In my mind and every system that I've worked on over the years, there is no such thing as too much return air to the evaporator coil. Once again, on the air conditioning side, refrigeration is a little bit different. So please remember that. All right, a window air conditioner. So here we have a picture of a window air conditioner. You guys have seen these things a lot of times. Okay, let's start with the outside. Well, let's go here to number 1, which is right here. The heart of the system is what? The compressor, right here. So we have low pressure, low temperature, vapor refrigerant coming back from the evaporator coil which is going to hit this compressor. This compressor is going to change the refrigerant from a low pressure vapor to a high pressure vapor. It is not going to change state at this point. Please remember, this compressor is designed to do what? Only pump refrigerant vapor. It is not, and I repeat, not designed to pump liquid. Okay, the next thing we need to look at is number 2. So on the evaporator coil, remember the design temperature on the evaporator coil is 40 degrees Fahrenheit. It absorbs heat from a 75-degree air room, as an example. But now as the temperature of the room falls, the ability to extract heat also is going to change as well. I cannot stress enough that this evaporator coil must be maintained, must be clean. If this thing is not cleaned on a regular basis, if the filter is not changed on a regular basis, if you have the incorrect fan speed, what is going to happen on an air conditioning process, this thing is not going to function properly. One of the things that I always see a lot on window units, I don't work on them too much anymore, but window units, number one problem I see here in Southern California is dirt, dirt, dirt. A lot of people say, well, the Freon is not flowing or the compressor's not working. In some cases, that's true. Number one thing I see with window air conditioners is this evaporator coil is plugged up with dirt. The filter hasn't been changed. Of course, the filters they put on these window units leaves a lot to be desired. The other thing that's wrong is on the condenser coil. These things are loaded up with dirt. So if you have a window air conditioner that you haven't serviced in a few years, well, what do you mean, Larry? You're supposed to service these things? Yes, you are. You're supposed to pull that chassis out of that cabinet, take it outside, get a garden hose, get some simple green as a chemical, and take and clean those coils. If you don't do that, that air conditioner is not going to operate at its peak efficiency. So, number 2, we have the heat entering the evaporator coil, and at that point, the refrigerant is coming from this the high side of the system through this metering device. In this case, they are showing a capillary tube. So basically, what is happening is this refrigerant has gone from a high pressure liquid to a low pressure vapor. When it goes to a low pressure vapor, it is boiling off, basically absorbing the heat that comes from the room, and then of course the absence of heat is cold. So we go in at 75, we come out at 55. So ideally our temperature splits should be this. They should be a 20-degree split going in, going out. When you check an air conditioning system, I don't care what refrigerant's in there. I don't care if it's 410A, if it's R22, if it's 422B, it doesn't matter. This is the end result. Air going in, air going out. You need to see at least a 20-degree difference. This is a rule of thumb that I've operated with for the last 40+ years. It's been around for a long time. This is a quick way to find out if the system is putting out. There are other things we have to check as well, but this is the first key that we need to look at. Okay, so now we've taken this refrigerant, we've boiled off we've absorbed the heat. The refrigerant changes from a liquid to a vapor, low pressure vapor, goes through the compressor, which is designed to only pump liquid, not liquid, but vapor. Low pressure vapor, change it to a high pressure vapor. Now we go to the condenser coil, and the condenser coil is going to give up the heat to the surrounding area. Notice that in this case here, the outdoor coil is designed for 125 degrees Fahrenheit and give up heat to 95-degree outside air. Now, as the temperature of the outside air goes up, basically that will have an impact as far as giving up that heat to the surrounding area. In very, very hot areas, this can be a problem sometimes. Sometimes we have to increase the airflow, we have to do other things in order for that heat that was picked up inside to get rejected to the outside. So once the refrigerant has come into this condenser, remember it's in a vapor state, and of course we are giving up the heat that was absorbed in the evaporator coil to the condenser coil. Assuming this thing's nice and clean, we're going to be able to take and drop out that heat to the surrounding area outside the building. Now, typically, what am I looking for as far as the split between the temperature in and the surrounding air? I think a good rule of thumb would be this, 10 degrees. So in other words, let's say that it's 95 degrees outside and the fan is blowing air across that condenser coil. You should see at least 10 degrees increase from the surrounding air. And that's just another rule of thumb that I've used, and it works very well. Hopefully this answers your questions as far as the window air conditioning unit. Remember, fan speed plays a big deal when it comes to regulating how much airflow is coming across the evaporator. If the airflow is too low, this thing's going to freeze up. If the airflow is too high, you're not going to get the correct cooling ratio. Temperature and pressure relationship. Some facts: water boils at 212 degrees at atmospheric pressure. That's assuming it's sea level. Or we're going to look at 29.92 inches Hg. Okay, this is going to be our pressure limit on where the water boils. Remember, if you go to Big Bear Lake or someplace high in the mountains, now this temperature drops as you go up in elevation. Water boils at 250 degrees if the pressure is increased to about 15 psig. Water boils at 40 degrees Fahrenheit if the pressure is reduced to 0.248 inches of vacuum. So what are we saying? When we take and use a vacuum pump to take and extract air, we're also going to extract moisture out. And what I mean by that is simply this. Air contains moisture. We want that moisture, especially in R410A systems, to be gone. We typically use a term micron level, which will be discussed later on. Refrigerants, pressure, and temperature. Refrigerants are substances that boil at low pressures and temperatures and condense at high pressures and temperatures. Saturation temperature point at which the addition or removal of heat will result in a change of state. And we're talking about the refrigerant now. During the change of state, the temperature remains constant, does not change. Refrigeration components. You should know this, but we'll review it once again. Evaporator absorbs the heat from the area to be cooled. The compressor creates the pressure difference needed to facilitate refrigerant flow through the system. In other words, it's a pump. And remember, once again, the compressor is designed to pump vapor, not liquid. Condenser is going to reject the heat that was picked up in the evaporator coil. The metering device can be a capillary tube, can be a piston, can be a thermal expansion valve, could be an electronic expansion valve, regulates the refrigerant flow to the evaporator. On the newer systems, I utilize, as an example, a field piece, either a 360 or 460 digital manifold set, which we have in the lab. And what we're going to observe when the system's being charged or checked, that expansion valve in this case is going to open and close. We're actually going to be able to see that based on the superheat and subcooling and the pressures on the system. We'll actually see those increase, decrease, telling us at service tech that this system is working properly. Evaporator, the heat exchange surface used to absorb heat, located on the low pressure side of the system between the metering device and the compressor, operates at temperatures lower than the medium that's being cooled or conditioned, absorbs heat by boiling at a low temperature liquid into a low temperature vapor. Now I need to say this about evaporator coils. If you don't have the proper airflow across that evaporator coil, it's going to freeze up. If the evaporator coil is located with dirt, is filled up with dirt, it's going to freeze up. And your ability to extract heat from a product or from the air is reduced correspondingly based on the amount of dirt or lack of airflow. It is critical to keep the airflow at a correct level, it is critical to keep that coil clean. If the coil is not clean, your ability to extract heat is impacted. Bottom line. Evaporator and refrigerant. The refrigerant typically enters the evaporator as a liquid vapor mix, 75% liquid, 25% vapor. Superheat. This is a term you're going to see a lot. The heating of the vapor above its saturation temperature ensures that no liquid refrigerant enters the compressor. On the gauge manifold sets that you guys will be using in the lab, we are going to be utilizing, as an example, a field piece, either a 360 or 460. There's other brands also available. Those digital gauges have clamps which are going to take and measure superheat and subcooling. We do monitor the superheat. If the superheat is too high, then here's what the problem is. You're not going to get the net refrigeration or air conditioning that you are looking for when that system is operating. What do I mean by this? It's very simply this. Basically, the superheat has to be kept at a certain level. If the superheat drops down too low, then basically what happens is compressors, as we said earlier, are designed to pump vapor. They're going to be pumping liquid instead. And when that happens, you're going to have all kinds of problems. We don't want to pump liquid refrigerant. We want to pump vapor. This is ensured by keeping the correct amount of superheat on that evaporator coil so that no liquid enters the compressor. Evaporator and superheat. Superheat is equal to the evaporator outlet temperature minus the temperature at which the refrigerant boils. So basically, you're going to have the saturation temperature, which is published for the refrigerant used, and the actual measured temperature. And the difference between the two is going to indicate the superheat value that is applied at this particular instant. Superheated vapor does not follow a pressure-temperature relationship. So please don't look for a chart trying to figure out superheat. This is calculated based on the refrigerant, the its corresponding saturation temperature versus the actual temperature. It is very important you have accurate thermometers in order to take and measure superheat. All right, here's a picture of an evaporator coil in a walk-in box. Here's your fans. Of course, the evaporator coil's on the back side. Down here we have the drain line, which the condensate, which from the refrigerant, from the air that's being extracted is going to give up moisture. It's going to go through this drain and exit the box. The compressor pumps heat-laden vapor from the evaporator to the condenser by increasing refrigerant pressure, reduces the pressure on the low side of the system, increases the pressure on the high side of the system. Compressor types, this will be talked about more later on. Different compressor types include the scroll, reciprocating, rotary. There's also the screw compressor as well as the centrifugal. Positive displacement compressors require that the compressed gas be removed to the condenser. So if you have a compressor, whether it be a reciprocating, whether it be a scroll, whether it be a centrifugal, this is a positive displacement compressor and it requires compressed gas be moved to the condenser in order to remove the heat that was picked up in the evaporator coil. All right, here we have pictures of rotary and scroll compressors. Now in this on this case here, figure 3.22, the rotary compressor with the motion in one direction and no backstroke. Notice that we have a spring that's applied to a blade or a valve here. Suction gas enters here, and the gas is going to take and be compressed through this off-center operation of the rotary compressor. And so what happens is, based on as this thing's rotating around, it is going to cause the suction valve to shut automatically and pressure to build up in the form of discharge superheated gas, and that'll be moved out. and basically go into the condenser coil as a superheated vapor. Once again, compressors are designed to pump vapor, not liquid. Once again, compressors are designed to pump vapor, not liquid. Please, please don't forget that. So, rotary compressors, you're going to see these on automotive. You're also going to see these a lot on window air conditioning units. I also see them on mini splits. They're used in small tonnage type systems. I have seen them used in commercial air conditioning, but typically they're going to be less than 5 tons or 60,000 BTUs as an example. You will not see a rotary compressor on a large installation of any kind. Over here, this is an example of a scroll compressor. You have basically two parts. One is the fixed scroll, which stays stationary, and then what they call the orbiting scroll. And this scroll is designed to actually compress gas. So basically what's going to happen is it is going to take and compress this refrigerant vapor, liquid, and basically it's going to utilize the orbiting scroll against the stationary scroll in order for this thing to happen. One thing about scroll compressors I should point out is the scroll compressors by design will spin backwards when the compressor shuts down. The early models had this uncanny noise. It made kind of like a type noise when it shut down. This has been corrected in newer models utilizing a check valve to prevent the refrigerant flowing in reverse condition. So in this case here, remember refrigerant now is going to go in the fixed scroll at a low pressure, low temperature vapor. And of course this orbiting scroll is going to compress around the stationary one, and it's going to take and push the refrigerant vapor through this center hole, and that of course will exit the compressor in the form of superheated gas. The condenser rejects sensible latent heat from the system, which was absorbed by the compressor and the evaporator. Located in the high pressure side of the system, the refrigerant condenses from a high temperature vapor to a high temperature liquid. Condensing temperature and subcooling. Condensing temperature is determined by the high side pressure in the system. Refrigerant is subcooled at the outlet of the condenser. This is a very key term you will utilize in air conditioning systems today. We are very, very concerned about subcooling. When we take in charge an air conditioning system, this subcooling is extremely important. Depending on the size of the system, the capacity of the evaporator, the refrigerant charge, I will just tell you as an average, we usually like to see on the subcooling side, the outlet of the condenser, we typically like to see anywhere from 9 to 13 degrees of subcooling to indicate that the unit is charged properly. This of course is assuming a 40-degree evaporator coil and a clean outdoor condenser, and typically 95-degree day, that kind of thing. We want to make sure that the units are charged properly. It would be my guess, and I've seen documentation on this, where a lot of air conditioning and refrigeration systems are improperly charged. And the reason why I say that is there's still some school of thought where just pressure gauges alone can determine if the system's charged properly. I used to be of that mindset. I no longer am. I utilize electronic gauges all the time, because that way we can get our superheat, get our subcooling, we can actually look at the refrigerant that is in the system, and we can determine and plot it and figure out if this system is at capacity, if it's charged properly or not. One of the things that you're going to find on a very hot day, especially in 410A systems, if the system's not properly charged, you will hear about that in the form of a service call saying that that air conditioner doesn't seem to be very cold anymore, and if your refrigerant charge is supposed to be 13 pounds and it's down to 8 pounds, you got a problem. First of all, you need to find and fix the leak. not just add gas and get it up to the proper subcooling level. You need to find and fix the leak. Once you find and fix the leak, then you add the proper amount of refrigerant. And of course, the evaporator coil has to be clean, and the condenser coil has to be clean, and the proper airflow across the evaporator as well as the condenser has to be maintained. So, subcooling, again, is the cooling of liquid refrigerant below its saturation temperature, is determined by subtracting the condenser's saturation temperature, which you're going to find on a PT chart, from the condenser outlet temperature. Once again, I love those field piece digital gauges because it does all that work for you. Basically, you just dial in the refrigerant that you are utilizing, whether it be R22, R410A, whatever. It's already built into the refrigerant pressure temperature charts that are stored digitally inside the gauge, and then basically by hooking it up, it'll automatically tell you where you're at. Process of subcooling. Okay, so basically we got refrigerant vapor coming from the evaporator coil. Of course, the compressor changes that low pressure, low temperature vapor to a high pressure, high temperature superheated vapor. And notice that the temperature goes up dramatically. And we typically are shooting for 125 degrees Fahrenheit across this evaporator coil. This basically shows where the first point of liquid takes place. Liquid doesn't occur till right about here it starts. It doesn't start right up here. It starts about down here. And as you can see, it travels in these U-shaped bends. Notice that the temperature stays the same, okay? Temperature stays the same until it gets to about 3/4 of the way down. Now the temperature drops off to 120 degrees Fahrenheit. And then when it leaves the condenser, notice that the temperature drops when it's fully liquid at 110 degrees. And at this point, we now have subcooled liquid. And this subcooled liquid ensures that the metering device has no liquid slash vapor. It is a solid column of liquid. You want a solid column of liquid refrigerant, because if you don't have that, what is going to happen is you're going to have problems with the refrigerant being able to pick up the heat in the evaporator. So the saturated liquid starts about right up here, and once we leave the condenser, we should have liquid and liquid only. Refrigerant in the condenser. The three important things may happen. Hot gas from the compressor is desuperheated from hot discharge temperature to the condensing temperature, sensible heat transfer. Remember, sensible is the heat that you can measure and feel. Refrigerant is condensed from a vapor to a liquid, in this case hidden heat. Latent heat is always referred to hidden heat, which you cannot measure. Liquid refrigerant temperature may be subcooled. Sensible heat transfer process is employed in this. Refrigerant metering device controls the flow of subcooled liquid from the condenser to the evaporator, creates a pressure drop between the high and low pressure sides of the system. About 25% of the liquid leaving the metering device is immediately vaporized flash gas. Commonly used metering devices include the orifice, which is a piston, capillary tube, which is a long, small copper tube. Automatic expansion valve works off pressure only, the actual refrigerant pressure. Then you have the thermostatic expansion valve, which has a bulb which is located on the suction line, which is going to measure the temperature of the refrigerant leaving the evaporator. And by doing this, the valve opens and closes in order to maintain the correct amount of superheat and keep that evaporator coil properly working as far as opening and closing is concerned. Electronic version of the expansion valve. Now we utilize sensors instead of bulbs, and this is all done digitally. On your mini splits, this is what we use. On some room air conditioners, this is what we use. But we are utilizing more and more electronics because it's more accurate and it does a good job. But it has its own set of challenges to go with it. Okay, the orifice. Old air conditioning systems as well as some refrigeration systems. Notice that coming through here we have 100% subcooled liquid. We're at 446 psi-G. Now we put in a orifice right here. Now with that orifice, look what happens. now we have a partial liquid 75% and a partial vapor 25%. And in this case here, we are measuring 120.5 psig. Over here on the liquid, high pressure, high temperature side, 446 psig. And basically what we are looking at in the liquid line is 41 degrees liquid and vapor at 120.5 psig. Refrigeration system and components. So basically, remember the whole idea is to take and absorb the heat in the evaporator, send it to the outside of the building. Here we have an example of a split system here. Room air is 75 degrees. Look at the relative humidity, 50%. You're comfortable at this point. If this percentage goes above 50%, then we're going to say we have an excessive amount of humidity. And some days we've had this summer, we've had higher than normal humidity levels in the air, and as a result, results in us being very uncomfortable. Now, here we have high temperature, high pressure liquid at 446 psig. Notice right here, we have 105 degrees. We have a solid column of liquid. The metering device is located here. In this case, we're going to assume this is either a capillary tube or a piston. We have a pressure drop that takes place here, and we now have about a 75 to 25% liquid versus vapor match here as far as the system working. So the refrigerant flows through the evaporator coil. Remember, we still have liquid at this point. We're at 118 psig, and we're still maintaining 40 degrees evaporator coil. We go through this way, then we go through this way. Temperature still being maintained, and as we get down, basically what happens to that liquid refrigerant, it boils off because it's absorbed heat. It boils off because it absorbs heat. Very important statement here. Notice that the design temperature of air conditioning is, once again, 40 degrees, 40 degrees. Now, the condition of the refrigerant is now measured at 50 degrees Fahrenheit. So basically, by looking at this, I can basically say we are probably looking at about 10 degrees of subcooling at this point. Now we're bringing this low pressure temperature refrigerant vapor back to the compressor, and of course then we leave the compressor as a high pressure, high temperature vapor. Notice we're at 200 degrees Fahrenheit, 446 psig. We now enter the condenser coil. We're now at 125, and over here at number 9, basically notice what happens to the refrigerant vapor. It is cool because we're surrounding cooler air to that high temperature, high pressure gas. As we're doing this, that refrigerant vapor gradually turns into liquid, and once we come back down here towards the end of the condenser, now we have liquid refrigerant. So basically the red's going to indicate the warm, hot refrigerant, blue is going to indicate the cold refrigerant. So remember, vapor here, and we're going to have vapor all the way up to the condenser. And basically once the condenser goes through its process of removing heat from the refrigerant, then basically this cycle repeats itself. Refrigerants, R12, that stuff's been gone since 1995. That contained, I don't know if you remember, but R12 was used in automotive air conditioning as well as domestic appliances, and in some cases used in air conditioning. And basically it was used for high, medium temperature, and 1996 this stuff went away. R12 is extremely hard to find today. There are a few systems still out there. I have not charged an R12 unit in probably the last 20 years. So I don't see it anymore. There's very, very few of them left. R22 is primarily air conditioning applications. Production ended in 2020. And what's interesting is, I don't know if you've looked at the price tag of a 30-pound jug of R22. When I got into this business in 1974, R22, I could purchase a 30-pound bottle for about $25. That same bottle with 30 pounds of R22, right now it's going to run me anywhere from almost $900 to $1,200 for that same bottle. If you have R22 in your service truck, lock it, cap it, keep an eye on it, because stuff is a valuable commodity since R22 is no longer used on new systems. R500, another refrigerant. This would be a blend. In R502, these were CFC refrigerants. They went away in 1996, as well as R12, which was a CFC, which means it contained chlorine atoms. R134A is a replacement for R12 with retrofit. So you can retrofit an old R12 system with R134A. Problem with R134A is considered an HFC, and they're now going to start phasing that out in favor of low global warming type refrigerants. Replacements for R22 include 410A and R407C. Now, I need to make a disclaimer. They're in the process, starting next year, we're going to start reducing the amount of 410A that is going to be manufactured. 407C, I do not know, because that's also a blend. But 410A is used on air conditioning systems today. Is it a good refrigerant? Yes, it is. Does it operate at higher temperatures, high pressures? Yes, it is. Our 410A is going to be phased out over time. And the reason why it's going to be phased out, it's based on the high global warming impact that the refrigerant has if it leaks out into the system. So leaks out of the system into the atmosphere. And because of that, there is an issue with 410A HFC type refrigerants, which we'll talk more about later on. Refrigerants have to be safe. They're designed to protect people from sickness, injury, or death. Proper ventilation is required. Modern refrigerants are non-toxic. When burned, toxic corrosive gases are created, and obviously they can create problems for anyone near around that. I was in the U.S. Navy for a number of years. We had a situation on the USS Bainbridge, which was based in San Diego back in the 80s, where a refrigeration system developed a leak. And one of the things that happened was this refrigerant, when it leaked into this compartment, and remember, on a ship, you don't usually have good ventilation in compartments that are 4 or 5 decks below the main deck. So, what am I saying? We had a situation where the refrigerant started leaking out as an alarm went off in a particular compartment, and people were sent down to, a person was sent down to this compartment where the refrigerant was leaking out. He was instantly overcome with heavy refrigerant collects towards the floor, and he did not have an oxygen breathing apparatus, and so as a result he lost consciousness and fell to the deck of the floor of that compartment. One of his sailor buddies happened to notice that he was in trouble, and he saw that the compartment door was open. He went inside to try to rescue him, and unfortunately same thing happened to him. And this situation repeated one more time. A total of 3 sailors lost their lives that day because of the fact that there was refrigerant leaking out, displacing the oxygen inside the compartment. All large air conditioning refrigeration systems today, whether it be naval or commercial, are required to have alarm systems which will locate, tell you where the leak is at in a compartment, and to evacuate that air. Fresh air is the best counterpart to refrigerant. Remember, leaking refrigerant is usually going to come out as a vapor, and it will basically affect your health. Got to be careful. You need to have what we call a oxygen breathing equipment available so that you will be able to not be overcome by lack of oxygen. Remember, the human body is required to have 19.5% oxygen by volume. If the oxygen is displaced, refrigerant, vapor, liquids, whatever, could enter your body and cause very bad results. Refrigerants must be detectable. Methods used for detecting leaks. Soap bubble solution pinpoints leaks. Works good most of the time. I use simple green because it's a little bit cheaper, and you can just use ordinary liquid soap and dilute it. The halide leak detector uses an open flame. This is no longer allowed because if that flame comes in contact with the refrigerant's going to change from a green to a blue, or I should say from a blue to a green. And what happens is that refrigerant's going to decompose, and in that decomposition, and I'm talking about HCFC refrigerants as well as HFC refrigerants, basically you're going to break down the chemical compounds. You'll end up with phosgene gas, and if you don't have oxygen breathing equipment on, I guarantee you will be overcome and you'll get very sick and possibly die as a result. Electronic leak detectors is good for finding the leak in a general area. I have a what they call a halogen specific electronic leak detector made by Fieldpiece. Works very, very well, and it's usually good for finding leaks. But the problem with it is there has to be a refrigerant in the sample that is hitting the sensor in order to detect where the leak is at. Ultraviolet leak detector is going to pinpoint the leak. Here's the one I really, really like. Ultrasonic leak detectors. It uses sound waves, and it's basically like having a super sensitive microphone in this sensor tube, a sniffer I should say, and you wear a set of headphones. I had the best luck trying to find small leaks with this right here. If I was to tell new people what is the best leak detector, go with this, ultrasonic leak detectors. These things work beautifully. What I like about it, you don't have to put a trace gas in. If you take a system that's completely flat on refrigerant, instead of mixing a small amount of refrigerant with nitrogen, you just take nitrogen, because nitrogen is an inert gas. It does not hurt, contaminate anything. You pressurize that system and you use this ultrasonic leak detection method. I guarantee you it will pinpoint and show you where the leaks is at, and you'll be able to identify and fix the leaks utilizing this concept. So my number one choice is ultrasonic. The next one would be your electronic leak detector. Soap I always use, that's a good old standby. Right, general refrigerant notes include should boil at a low temperature at atmospheric pressure. It is illegal to intentionally vent refrigerants to the atmosphere. Stiff fines for violations. This is covered under, I believe it's a Code of Federal Regulations, CFR 40, which was part of the Montreal Agreement back in the early 90s. And there's the Clean Air Act of, I believe it's 1990. That was signed by former George Bush, the president, and basically what happened was it mandated certification for the technicians, and also established a schedule for the phase out of CFC refrigerants, HCFC refrigerants, and now it's been amended again, and we're going to be seeing the phase out of HFC refrigerants. So you guys getting into the trade, 20 years from now, you probably will see very little HFC refrigerants. CFCs are long gone since 1996. HCFC refrigerants have been no longer made since the year 2020. But bear in mind, millions of air conditioning systems in the United States still utilize HCFC refrigerants. And refrigerant phase-out schedules have been published by EPA. You need to, as a service tech, be aware of the updates as they occur, because it's like everything else in this world, the schedules either get moved up or moved back depending on the type of refrigerant. So what you think is good and plentiful today may be in short supply tomorrow. And it's based on market conditions, it's based on environmental factors, things like that. Refrigerant cylinder drums are color coded. So typically when we're recovering any refrigerant, I don't care what it is, I don't care if it's R22, if it's 410A, typically you're going to utilize a predominantly gray with a yellow top recovery bottle. Recover, recycling, and reclaiming of refrigerants. Recovery is mandatory during service and installation operations. We'll be doing this in class as projects, and I'm going to insist that everybody has a chance on learning how to recover refrigerant out of the system. You must utilize a good recovery unit. You have to have a scale in addition to the bottle, leak-free hoses, and there is a process involved. But I don't care what system it is, you're supposed to take and pull out the refrigerant of the system prior to disposal. You have an old system, you recover the refrigerant out, you have to identify it. Once a refrigerant bottle is 80% full, you have to discontinue recovery operations, get another bottle, and continue the process. Large systems are going to use larger refrigerant recovery bottles. I can't emphasize enough, you have to have an accurate scale in order to take away the cylinders and check the progress. Fieldpiece has a nice scale where it has a wireless setup, so it'll actually go to your app on a phone, and you can monitor how that bottle is filling up as you're working on a system on recovery. Typically, on residential air conditioning systems, you're looking anywhere from 6 to 13 or 14 pounds of refrigerant being recovered on a system prior to disconnecting, replacement, disposal, that kind of thing. Okay, the intention was to reduce the emissions of CFCs, which we have because they're no longer made, no longer utilized for the most part. HCFC refrigerants, example being R22, and HFC refrigerant, example being R410A. Now, the problem, like I said, with HFC refrigerants, such as 410A, such as R134A, is they contribute significantly to climate change, and as a result, HFC refrigerants are going to be reduced and eventually banned. Recovery equipment must be used according to the manufacturer's instructions. The only thing I want to say is there are good recovery machines out there and there are poor recovery machines out there. We will cover the proper use of how to recover refrigerant out of a system with the equipment that we have in the lab. Plotting the refrigerant cycle. Pressure enthalpy chart creates a graphical presentation of the system. The pressure scales on a vertical axis, which will be illustrated as PSIA, which is your pressure absolute, and your enthalpy, which is basically the enthalpy scale along the bottom of the chart. Remember, this is going to be your sensible heat plus your latent heat, which you cannot measure. The horseshoe curve represents the saturation curve. Refrigerant is saturated under the curve. Enthalpy is defined as heat content. You look at these charts here. This is a example of how a pressure temperature enthalpy diagrams, or PT charts, are utilized. When I got into this business 40 plus years ago, this was the hard part for me to understand initially, but over time, you understand what the pressure enthalpy charts are used for. You can actually plot an air conditioning refrigeration system at any given point of the system to see if it's operating correctly. So this basically shows you the saturation line under enthalpy, lines of constant quality vapor as a percentage over here. Then you're going to have lines of constant enthalpy. Down here, you're going to have lines of constant specific volume. Over here, you're going to have lines of constant pressure. Notice it's illustrated in PSIA. Remember, you're going to take a pressure, you're going to add 14.7 or 15 to that number in order to come up with PSIA. Then you have the lines of constant enthalpy over here, lines of constant temperature, and this looks like isotherms. And up here you have your subcool, saturated, superheat regions. So this we can take and plot, see what the refrigeration air conditioning system is doing by utilizing these charts, measuring the temperatures and recording the pressures. I can't stress enough, you must have accurate instruments in order for this to happen. If you do not have accurate instruments, you are going to get bad readings. You're not going to be able to plot a system. Pressure enthalpy diagram of refrigerant blend. Blends are a little bit different. Basically, a blended refrigerant has more than one refrigerant in its chemical mix. And here's what the problem is. With the refrigerant, and I can't emphasize this enough, if you have a blend, let's just use as an example R407C, that is a blended refrigerant. It consists of two different chemicals, if I remember correctly, and the problem is there's an exacting process in the manufacture of this refrigerant when it is blended together in the process of making this refrigerant. If the refrigerant is put into a system, and then let's say over time a leak develops, now the refrigerant that was in the system is leaking out. Well, here's what happens. The refrigerant pressure temperatures change based on the leakage rate. So what happens is if you thought you had 407C and 90% of it has gone out, you still have some of the refrigerant in there, you basically cannot ensure that the chemical composition of the remaining refrigerant is still valid. And at that point you have to take out what is left, then you have to fix the leak, and then you charge with new refrigerant. So it's very critical that the refrigerant chemical mixture is maintained. If you have a leaking system, that is not assured, and you're going to have a problem. This chart here illustrates the pressure enthalpy diagram of a refrigerant blend with a noticeable temperature glide. Okay, and the glide is going to show you in a near azeotropic blend, and basically what is going to happen is instead of the pressure temperature being a flat line or in a how do I say this, refrigerant is going to not go in at a gradual angle. You're going to have dips and valleys with this glide. Basically, what am I saying with glide? The refrigerant temperatures and pressures change as the refrigerant is exposed to the atmosphere, or in this case, if the refrigerant is boiling off, it is not going to be a uniform boiling temperature pressure relationship. It's going to change.